Okay, so now we're going to take a look at the a second combination, which is a weak acid strong base titration. So this is our weak acid strong base. So here we're going to be starting off with a weak acid and then titrating a strong base like sodium hydroxide against it. Now, we mentioned before that the first thing we need to consider is the difference in the shape of the titration curve. And what we see here that's different than in the strong acid, strong base, is that the initial pH is actually higher than the strong acid, strong base titration. So remember, that was like around 1 in a strong acid, strong base. The other difference is that there's this initial portion here is different as well, which we'll talk about in a little bit. And what we'll also see is that what's similar is we do have this region where there's a big change, a drastic change in the pH over a small volume of NaOH that was added. And right in the middle is going to be the equivalence point. And the equivalence point for strong acids, a weak acid, strong base tends to be on the basic side, whereas for the strong acid, strong base, okay, the equivalence point is actually right at 7 at the neutral pH, right? So that's two or a few differences between the strong or the weak acid versus the strong base titration. So let's take a look at some of the other differences between them. So we have here the a weak acid such as acetic acid. We know that the acetic acid can react with any added hydroxide ion to produce. So this loses the H plus, combines with the OH minus to make H2O, and then we get the conjugate base, right? So this is our acid here, and we get the conjugate base as one of the products. That conjugate base that results, the acetate ion, can undergo hydrolysis. So it reacts with water. Remember now, water is the H2O. This can accept an H plus from water to act as the conjugate base. That's what bases do. And as it does that, we end up producing the acetate ion, I'm sorry, the acetic acid, and then we also get the hydroxide ion as well. So what this means then is that at the equivalence point, when we only have the acetate in solution, this thing here, because it's an aqueous solution, it will react with water to produce the acetic acid, and then we also get the hydroxide. So it forms a hydroxide ion, and as a result, the pH is going to be greater than 7 at the equivalence point. Right, and that's why, I'm sorry, scroll down, that's why the equivalence point is higher. It's over here as opposed to exactly 7 with the strong acid, strong base titration. So let's take a look at some calculations involved in determining the pH at each point in the addition of the strong base to the weak acid. So let's take a look first of all at the very beginning. So before adding any base to the weak acid, so all we have is just the acetic acid, and that's an equilibrium system. We can use our ice table to determine what X is. X is the H plus concentration, and we've done that already in a previous section. So the pH initially is just under 3, 2.87, and we saw that, let me back up here, in our curve, right? The pH is, yes, it's acidic, but it's higher than that for the strong acid, strong base titration. What happens further on in the titration? If I add a little bit more of if I start adding now some of the some of the strong acid to it. So let's again take a look at adding 10, let's say about 10 milliliters of the base. Okay, so if I add, so after addition of, let's say 10.0 mils of the NaOH. Okay, so the NaOH, I remember, is going to produce the hydroxide ion. What part of the weak acid system is going to react with it? Well, it's the acid portion, right? And that's the acetic acid here is going to react with the hydroxide to produce the acetate. And then we also get the water as the other product. So 10 mils of the NaOH, and the NaOH was a 0.100 molar NaOH solution. So again, we can use a little bit of solution stoichiometry, 10.00 mils. We have a 0.1 millimolar for every mil. Okay, so 10 times 0.1 would give us 1. 0.0 millimoles of the OH minus. Okay, and then what else do we have? We have originally here, we have the 25 milliliters of the 0.1 molar acetic acid, right? So we have 25 mils of the 0.100 millimolar for every 1 mil. Okay, so that gives 2.5 millimoles of the acetic acid, the CH3 COOH. So in my equation, we're going to have the following. So initially here, when I titrate that amount in, just calculated that I'm at 25 mils of the acetic acid. I'm going to have 2.5 millimoles. I'm going to add 1.0 millimoles of the hydroxide ion. These are going to react in a stoichiometric ratio. So we're going to use up all of the hydroxide. We're going to use up the same stoichiometric amount of the acetic acid. We're going to produce the same stoichiometric amount of the acetate ion. So then we end up with these concentrations. Because now we have pretty significant amounts of our acid and our conjugate base, we can treat this as a buffer system. Okay, and we can use the Henderson-Hasselbalch equation in order to solve for this. So the pH then, with the pKa for acetic acid, 4.74 plus the log of the conjugate base, 1.0 over the acid, 1.5. When we solve that, we end up with a pH of 4.56 after we've added that 10 milliliters of the sodium hydroxide. Right, so we can do that, incrementally until we get to, let's say, the equivalence point, right? And at the equivalence point, all of the acetic acid would have been neutralized. Okay, so if all of the acetic acid is neutralized, what we're left with then is going to be some of the acetate ion in solution. Now, we're also going to have the sodium ion, but that doesn't affect the pH because it doesn't undergo hydrolysis. So all we really need to consider is the acetate ion. Okay, so all of the acetic acid is used up at the equivalence point. And we'll have some of the acetate ion left over. So the pH then will be determined by the Kb of the acetate ion. which is the base ionization constant of the acetate ion, which is the CH3COO minus. And the equivalence point occurs when 25 milliliters of the base, the sodium hydroxide, has been added, making the total volume equal to 50 milliliters. So let's take a look at how we do this. So we have our equation that shows how the hydroxide ion reacts with acetic acid, right? So we have the same equation we've seen previously above, neutralizes it to produce the acetate ion, we get H2O. So originally we have our 25 mils of the acetic acid in the flask, so that gives us the 2.5 millimolar. At the equivalence point, we've used 25 mils of the sodium hydroxide with the 0.100 molar concentration. So we use our solution stoichiometry, determine the number of millimoles of the sodium hydroxide, which is 2.5. These are going to react in a 1-to-1 mole ratio. So we use up the same stoichiometric amount of these. We're going to produce the same stoichiometric amount of the CH3COO minus. Right, so we have at equivalence point now, we just have the acetate ion that's left over at that point. So this is left over here at the equivalence point. And the total volume that we've used here now, we've added 25 mils of the sodium hydroxide to the 25 mils of the acid. So 25 plus 25 would give a total of 50.0 mils. We have 2.5 millimolar. So the concentration then of the CH3COO minus would be 2.5 millimolar for every 50.0 mils. Okay, so we evaluate that and we end up with 0.050 molar as our concentration of the acetate ion. And that's what we're left over with at the equivalence point, right? We can then write an equilibrium expression for that as follows. So at equilibrium now, or with that equilibrium expression at the equivalence point, that acetate ion will undergo hydrolysis, act as a base, accept the H plus to produce hydroxide. We also get the acetic acid back. Initial concentration here, we just calculated it, 0.050 molar. And then we do our regular thing, our ice table. We're going to lose X amount. We're going to gain X amount of these. We can then write our expression for this. Now, this is acting as a base. So this would be our Kb expression. We can look up the Ka for acetic acid. And so using the Ka value, we can look up for acetic acid. We can use the relationship where Ka times Kb is equal to Kw. So then our Kb would be equal to Kw divided by Ka. And we can determine that ends up being 5.6 times 10 to the negative 10. And that will be equal to the OH minus concentration times the acetic acid concentration divided by the acetate ion concentration at equilibrium. So these are these values here. We end up with X squared over 0.050 minus X, again, assuming X is small. And we solve for the OH minus concentration. And that ends up being 5.3 times 10 to the minus 6. We can determine the pOH, which ends up being 5.28. So the pH then would be equal to 14 minus 5.28, which would give 8.72. And that's why at the equivalence point, the pH is not neutral. It is actually on the basic side, right? It's right above 8.7, right about here. And that's because at the equivalence point in the strong base weak acid titration, you actually do have that acetate ion left over that will undergo hydrolysis to produce the hydroxide ion in the solution. After the equivalence point, after all the acetic acid has been neutralized, nothing is left to neutralize the added strong base. So as a result, it's going to look very similar to that of the strong acid, strong base titration after that equivalence point as well. Okay, so for each of the data points on our weak acid strong base titration, we could calculate the pH, and let's just summarize how we can calculate the pHs at each of those points. Okay, so for the weak acid strong base titration, prior to the addition of any base, okay, all this is this is an equilibrium problem that is solved using the concentration and the ionization constant. And an equilibrium table, right? Our ice table. So that's just when we have our weak acid present. Prior to the equivalence point, so after we start adding now some of the strong base, but before the equivalence point, this ends up being a buffer system. So what we can use is the Henderson-Hasselbalch equation to solve for the pH. And then finally, after the equivalence point, the titration curve of a weak acid is identical to that of a strong acid. Okay, so we need to identify, first of all, what type of titration is going on. Is it a strong acid, strong base? Is it a weak acid, strong base? And then we can use our tools that we've learned in order to solve for the pH at different points along the titration curve. So the other thing that we missed on here that I neglected to mention was we talked about before we added any base, and then before the equivalence point, well, we didn't really talk about at the equivalence point, which actually is a very important part of this. So at the equivalence point, this is also an equilibrium problem. Okay, which means that we're going to use our concentrations, ionization constant, and ice tables as well to solve for the pH.